Good morning, everybody. I'm going to presenting these special properties of polymer. It's mechanical properties of polymer. Before understood this, how it's behave with loading or pressing of polymer, how it's behave. We need to understand this term first. Stress and strain. Actually, these two terms is the size independent term. It's the stress called load, how much force is applied or dropped, and the strain is how much displacement is occurred. And the elastic behavior, and it's reversible. Within short range, if stress is applied, then straining occur. If we again recover this stress, then it will retain its previous shape and size. It's called elastic behavior. And the plastic behavior is the permanent shape change, the permanent deformations of the polymer material. And after certain point, certain stress, it becomes permanent deformation. And this certain limit is called the yield point. We will discuss later how it shows. And another two terms, toughness and ductility. How a polymeric material consume, how much energy they consume before the fragile or the cut-off. That energy represent in that properties the toughness and ductility, depending on its two different criteria. And hardness, how that material resists to deformation. That represent how much that material is hard.
한국 학생들 혹시 이해 안 되면 언제든지 스탑하고 질문하면 될 것 같고요. 이 스트레스라는 거는 우리말로 하면 응력이라고 해야 되나? 그러니까 오늘 하는 거는 이제 물질의 어떤 특히 고분자 같은 그런 것들에서 중요한 특성 중에 하나가 물리적인 성질이잖아요. 그러니까 물리적인 성질을 표현하고 물리적인 성질을 측정하는 방법에 대한 세미나를 이제 하는 거고, 스트레스라는 것은 그러니까 쉽게 얘기하면 말 그대로 그 물질에 주어지는 어떤 힘, 응력이라고 생각하면 되고, 스트레인이라는 것은 그 물질이 그걸 얼마나 흡수할 수 있는 저렇게 지금 늘어나는 스트레인 뭐라고 그러죠?
Strain is kind of
장력이라고 하나? 그러니까 얼마만큼 흡수할 수 있는지에 대한 표현이라고 보면 되고요. 그다음에 일라스틱이라는 것은 아는 것처럼 얼마만큼 이제 회복이 될 수 있는가를, 얼마만큼 우리가 힘을 줬다가 다시 났을 때 회복될 수 있는 거를 말하는 거고, 다 보면 알 것 같은데, 그다음에 그거에 대해 반대되는 게 이제 터프하다는 성질 또는 덕타이트, 터프하다는 건 당연히 그냥 힘은 강하게 받지만 일단 받으면 다시 회복 능력이 없고 다시 부러지겠죠. 그래서 그런 거를 얘기하는 거고, 강도라는 것은, 하드니스라는 것은 그거하고 조금 다른 표현이에요. 그러니까 일라스틱하고 플라스틱이 비슷한 개념이지만 살짝 다르듯이 터프니스하고 하드한 것도 비슷한 개념이지만 사실은 조금 다른 거죠. 그러니까 조금 여기 저 데피니션을 읽어보면 이해를 할 것 같은데. 오케이, go ahead.
And here is the four different kinds of stress and their respective strain. Stress or load, or strain or displacement. There are four kinds of tensile stress that called when it's unidirectional. This force is applied. As we know, the stress is similar kind of pressure, and the force per unit cross-sectional area is called the stress. And regarding this, we can found this unit megapascal or Newton per meter square or millimeter square. This is the stress. Here is the area that we found. And strain, it's a unitless dimension, because the strain we measured the previous how much the length was, and after applying stress how much is deformed. And from this subtraction value we can just measure how much, and the unit we use percentage. That's why there is no specific unit.
So please pay attention to this unit. As Jaffa just mentioned, stress has the force unit, whereas the stress there is a percentage. So how much of your material is actually elongated? 얼마만큼 늘어났는지에 대한 퍼센티지의 비율, 힘을 줬다가 얘가 힘을 놨을 때 얼마만큼 얘가 늘어났다가 다시 복원되는 그 정도를 나타내는 족도니까 퍼센테이지로 나타나고, 반면에 스트레스는 그 물질이 얼마만큼 견뎌낼 수 있는지, 내가 가는 힘에 대한 표현이니까 단위는 좋다. 그래서 이렇게 표현이 되고 있어서 단위를 좀 이해할 필요가 있습니다. 오케이, go ahead.
Usually we use this kind of tensile stress and strain, but few other methods they also use like compress, and it's quite similar to tensile stress. Instead of they are drawing or dragging, they are just pressed here and compressed there. Using that compress, there is maybe wide is increased. How much is increased and how much is shorten this length? Regarding this one, they maybe calculate this strain, how much strain is occur. And if any three-dimensional case, the shear stress we can found here. Just if force can apply to the surface of any plane of like cubic surface, then we call this shear stress. The layer, the below layer was stiff, but the upper layer is stressing. That called shear stress. And regarding this stress, there is some displacement of this molecular level, and how much angle it's tilt. From that angle tan theta, we can calculate this one strain. How much shear strain? We call that strain is called shear strain. And another stress strain behavior is found if like cylindrical. If we just rotate something like this one, there is maybe a torque is applied. Two different kind of forces applied, and this stress we can calculate using torque. As you know from the definition of torque, how much force is applied and how much distance the forces occur. Multiplying this force and the distance, we can calculate this torque. This is for torsion stress, and the strain is occur when we just torsion like is, then there is something very angle is twisted, and this twist angle measure the how much strain is occur. And from that case, the stress strain behavior can found. Usually, how it's behave like any material when we apply stress and strain. As I already mentioned, this one elastic deformation or elastic behavior, and already I told that it's a reversible process within short range, because if we exceed this yield point stress, then it will maybe permanently deform. That's why within this short limit, it's any material can behave elastic like. If we stress, then it displacement occur, I mean the deformation occur, but strain occur. If again we recover this stress, then it will retain this previous state, and this behavior is called elastic deformation.
So that is where described this reason, right?
Yes.
This reason. So he's applying, we are applying some stress, some forces, and that in this region, within this region, this is strain. So this polymer or any material can absorb and become elastic or deform or whatever up to here. So we apply here and get back. We apply forces and stop it and it will get back. So within this region,
Not this.
Up to P.
Up to P.
To P.
up to P. Okay, so there is a slope change. So yeah, so up to P, it's going. The slope is going linear. So up to P, it's fully recoverable. Which means that you apply the forces and you stop it. It will get elongated. You stop it and it will recover, just like rubber band. Right? And above this point, now it becomes some
permanent deformation.
permanent deformation. So it can be recovered,
But not fully.
yeah, not fully. So you already strengthened to some extent, so it cannot recover to its original shape or original materials. 여기까지는 그 힘을 주면서 이게 완전히 탄성을 가지고 있는 영역이고요. 그래서 이거는 힘을 주는 만큼 얘가 저기 늘어났다가 다시 퍼센티지만큼 요 퍼센트 늘어났다가 다시 힘을 놓게 되면 다시 돌아오고 힘을 주게 되면 더 늘어났다가 다시 돌아오게 되고 요 직선까지 가는 영역에서는 그걸 완벽하게 얘가 소화를 해내다가 고무줄 늘렸다가 놓으면 돌아가는 거죠. 이제 요 지점 그죠 변곡점이 생기는 요 지점부터는 이제 그 약간의 회복력을 잃어버리는 거죠. 그래서 여기서부터는 돌아올 수는 있지만 이제 그 원래 상태처럼 우리 이미 쫙 늘렸기 때문에 늘어난 풍선처럼 이제 그 회복력을 갖지는 못하는 영역이 요 영역입니다. 그래서 요게 아까 데피니션에서 봤던 것처럼 일라스틱은 완벽하게 그 원래의 성질을 가질 수 있는 영역이고 반면에 플라스틱은 그 흡수를 할 수 있지만 충격을 흡수를 할 수 있지만 그 보건력을 다시 회복할 수 없기 때문에 요 영역을 경계로 일라스틱이냐 플라스틱이냐를 정의를 하죠. 오케이.
And as I already told that plastic deformation is irreversible, and when we stress apply after yield strain, it will get deformed permanently, but cannot get rid of the previous state. And that's why it's called irreversible deformation, and it's plastic deformation. The other term I already told that yield strain is a theoretical point, and when the permanent deformation is appear 0.2%, that point was called yield strength, and this point we can calculate from here. But after that, any material shows permanent deformation or plastic deformation, and before that it shows the elastic deformation.
Say that again. So this yield strength is the point where the material loses what?
That point it shows permanent deformation up to
above 2.0,
not above, up to at least 0.2% here. offset.
그러니까 0.2% 이내까지 이 0.2를 벗어나는 그 디포메이션이 일어나는 지점을 yield strength라고 한다는 얘기야?
예, 그런 거죠.
이것도 처음 듣네. Okay, any point that material, so within this region is still your material is still plastic, so it may have some plastic, but there are, as mentioned, so within below this region there's no deformation. The material is fully recoverable. But after this region, the material becomes some deformation is occurring.
It's theoretical point, that's how we can calculate.
Deformation is above this percentage, then that point is called yield strength. Okay.
And usually in stress test curve, we can find this kind of graph, and we can divide it two regions. As I already mentioned that when up to this region, the stress and strain shows linear behavior. That area is called elastic behavior, and after that there is no like linear behavior, stress strain relationships that called elastic curve. The scientist Hooks make one linear relationship between the stress and strain, and he found within this elastic limit it shows proportional relationship with stress. As we increase stress, its strain will also increase, and when we equalize, then we can find one constant value. That constant is called modulus, and regarding this scientist name we call Young modulus. When we apply the stress in unidirectional, then we call it Young modulus, and its unit also we can measure by using gigapascal or megapascal or pound per square inch. And here is the simple diagram. If we force applied in unidirectional, then we may found like a strain. The previous structure was the black one, and after applying force, there is some deformation occur, and from there we can calculate this on the previous length and the deformation strain how much is occur, and from this one we can calculate this Young modulus.
Are you going to talk about any other modulus like stories and
Yes, sir.
like stories and
Shear modulus.
okay, can you go back? Again, the modulus is another feature which describes the material. So, and there are many different types of modulus, and Young's modulus is something that we mostly use. And other than Young's modulus, there are many other shear modulus or storage modulus or loss modulus, and there's many more. And it always gives a property of your material. But as you see from this Young's modulus, this is if you will understand from this equation quickly, right? So from that SS curve, which means stress and strain SS curve. So the Young's modulus represent the slope. So whether some material have this kind of behavior and some material have this kind of behavior, right? That gives a different information, right? So if the slope is different, right? If the material can have a slope like this way, some material have some like this way, but that from this S and S value, the stress and strain value, this slope and this slope cannot really represent the information of your material. So in order to demonstrate this kind of property well, the Young's modulus is described. So because if you calculate the slope, then it will give some information about how your material behaves. Understood that? 그러니까 이 SS 커브 아까 나왔던 스트레스하고 스트레인을 가지고 되게 성질을 측정을 하는데 그게 얼마만큼 늘어나고 얼마만큼 물성이 이게 힘을 견뎌내느냐에 대한 정보를 주는데 이게 이제 이렇게 누워 있는지 이렇게 서 있는지에 대한 거는 거기에서 사실은 좀 얻기가 어렵기 때문에 이제 그걸 나타내는 좋은 방법이 이 사람이 개발한 모듈러스라는 거고요. 그러니까 말 그대로 이게 이제 이렇게 이거에 대한 지금 보시는 것처럼 이거죠. 그 직선의 기울기입니다. 그래서 이 직선의 기울기를 계산을 함으로써 얘가 얼마만큼 누워 있는지 얼마만큼 서 있는지 그러니까 그거에 대한 정보는 또 다른 거라는 거죠. 물질 자체가 얼마만큼 그거 내가 주는 정보는 좀 다릅니다. If you see by definition, so this is a percentage, right? The stress is can be described as a length or a millimeter or whatever, inch or whatever. And this Y value was megapascal as we have seen previously. So this is percentage. If you divide megapascal by percentage, it will give a gigapascal, right? 그렇죠? 얘 단위가 메가파스칼이었고 얘가 퍼센트였잖아. 그러니까 이걸 다시 메가파스칼을 퍼센트로 나누면 곱하기 이걸 해야 되니까 기가파스칼이 나오지.
There is a need.
기가파스칼이 나오는 게 아니라 기가파스칼로 표현을 하지. 숫자는 곱하기 100이 아니라 10을 빼주면 되겠지. 오케이. Go ahead.
Usually we use this kind of modulus, but there is another case of modulus like shear modulus. When shear stress is applied, then the shear strain and the shear stress and shear strain, there is looks like a similar relationship between them, and we can calculate from this one the shear modulus. But like as if any liquid material or any solid material, if we press all directions, I mean in bulk, then we can call it bulk modulus, and we can found this one from using this equation. The volume changes and the previous volume. We can found the volume strain or this one, and from this one we can calculate. And if the material is isotropic material, I mean with stress and strain is, if we apply in the several directions, it show the similar behavior, then it called the isotropic material, and in that material we can make relation with the shear modulus and the Young modulus and the bulk modulus and the Young modulus like this way. And here n is the Poisson ratio. Another term I didn't mention here. Poisson ratio is when we apply any load of material, then it may elongate, deform. But as much as when its length is increased, there is some wideness is shrinkage. That means the wide is reduced. How much reduced with the length increase? The wide reduced divided by the length increase, we can get this one ratio, and this ratio is called Poisson ratio. And
can you go back? I don't know that much about the shear and bulk modulus, which we don't usually use, but anyway, that was good. 자, 이거는 우리가 잘 쓰지 않는 거라서 뭐 이게 있다는 건 알고 있는데 뭐 저기 나도 잘 모르겠고요. Can you go back? I think I missed one important thing. Can you go back? 자, 우리 AM 팀 생각하면 here, okay, stop. AM 팀 생각하면 AM 팀 우리 그 연료전지 그 멤브레인 팀의 과제 목표로 생각하면 전도도 하고 알칼리 안정도 하고 기계적인 성질이 있습니다. 그죠? 기계적인 성질이 S 값하고 S 값이 정해져 있죠. 우리가 목표를 하는 게 이게 내 기억이 맞다면 우리는 30메가파스칼이고 50인가? 50이고 바뀌잖아. 이게 30메가고 이게 the AM the target is 30 megapascal
and strain was 20%. 50%.
그러니까 이게 30 우리 AM 과제의 물성 그 고분자 많이 발전되는 물성도 그 타겟이 있는데 여기가 30 메가파스칼 50, 30 아닌가? 30 메가파스칼에 50%를 넘어야 되는데 그것도 중요하지만 이 영수 모듈러스도 들어가 있어요. 아니 영수 모듈러스
Young's modulus.
I forgot. 근데 예를 들어서 어떤 막이 있는데 어떤 막이 이 숫자를 다 넘을 수는 있어요. 다 넘을 수 있는데 이게 이렇게 가서 넘을 수도 있고 이렇게 가서 넘을 수도 있잖아요. 그죠? 그래서 영수 모듈러스 따로 주는 거거든. 이게 이렇게 가도 너무 이렇게 가도 안 되고 또 너무 이렇게 가도 안 돼. 이렇게 쭉 가서 이렇게 쭉 가서 이렇게 넘을 수도 있죠. 이렇게 쭉 가서 이 밸류를 넘을 수도 있죠. 얘도 넘고 얘도 넘을 수도 있죠. 반면에 이렇게 쭉 올라가서 이 물질이 이 타겟을 맞출 수도 있죠. 근데 그걸 보정하는 게 영수 모듈러스라는 거죠. 그래서 너무 물질이 이렇게 치우쳐도 안 되고 너무 물질이 이렇게 쳐도 안 되기 때문에 이 값과 이 값 더하기 영수 모듈러스 넣어서 영수 모듈러스도 적당한 범위 내에 너무 이렇게 가지도 않고 너무 이렇게 가지도 않는 이 범위의 슬로프를 가져야 된다는 의미에서 영수 모듈러스도 있어요. 그래서 세 가지를 다 맞춰야 되기 때문에 사실은 쉬운 게 아니라는 거죠. AM 목표를 이번에 다 1단계에서 다 맞췄지만 기계적 성질을 우리가 만족을 못하죠. In the AM project, the fuel cell membrane project, there's a target about the conductivity and alkaline stability, and there is also mechanical property of the stress and strain, plus Young's modulus. We can make a material of your membrane with the high targeted the material which shows the
ability.
But above these targeted as stress or strain. But you suppose that some material can have these behavior. Some material can have these behavior. So in both cases you can reach that target. But these two materials have a totally different mechanical behavior. And that is why they require Young's modulus. Because then the Young's modulus, this is not good and this is not good. So you need somewhere between with some stress and some strain. That is why that is an extra factor of the Young's modulus. Which so it's not that much that's not that much easy to achieve all this mechanical property. Okay, go ahead.
In this slide, actually, it's in case of metal how its atomic stage deform and how it looks like. Actually, this up to this region, it shows elastic behavior. When we force apply, then some material electron atomic deformation is occur. It sends this previous shape, but after remove this stress, it may retain its previous state. But when you show the plastic behavior, like this is an elastic plus plastic, then we found that up to certain atom is shape change, their position change. After recover this stress, it cannot may come to the previous point. It looks like this one if we found this. And at this point, as I mentioned, this yield stress, and it's called the permanent strain. Yield strain, plastic strain.
So there is this much of deformation.
Yes.
occurred, 그죠?
Yes.
이거 힘을 가할 때 났는데 이미 이 상태로 돌아오지 못하고 얘 때문에 이만큼을 늘어나는 거죠. 이만큼 디포메이션의 물질의 변화가 이미 있은 거죠. When you calculate the Young's modulus, when you say, suppose that you have this kind of behavior, when you have this kind of behavior, and when you need to calculate the Young's modulus, we don't take these values.
Yes,
We
just
straight
take transient of this one, and from this one we can calculate.
이 SS 값은 이제 내가 찾아야 되는데 그래프에서 내가 찾아야 되는데 이
when you calculate, just then now we write one straight line, and up to this point it shows
in the paper we usually report the stress at maximum, right?
Yeah, tensile strain. Tensile stress.
Tensile stress.
Yeah. The maximum stress. How much?
So here, right here, right?
Yeah.
Yeah.
I can show here the next
Maximum.
Maximum. How much stress is occurred?
So
Sometimes
here,
we have
yes.
like this one. Sometimes
Yeah.
we have this
Maximum.
one.
Okay.
The maximum value.
Okay. 자, 이게 그래프가 이렇게 지금 여기까지는 보온력을 가지다가 일라스틱 성질을 가지다가 여기서는 디포메이션이 일어났는데, 근데 이 디포메이션 된 영역도 중요한 정보를 주기 때문에 이거 스트레스를 내가 저 보고를 할 때는 요 지점을 하는 게 아니라 요 지점을 가장 스트레스의 최대값을 보고를 하고 거기에 해당하는 요 스트레인을 보고를 하죠. 근데 영수모듈을 보고를 할 때는 요렇게 찾는 게 아니라 여기서는 이미 변형이 있었기 때문에 요 직선이 생기는 여기에 여기를 잘라서 여기까지만 슬로프를 구합니다. 맞지? 내가 틀리면 좀 맞지? 틀리면 좀 지적을 해주고. So suppose that we have this kind of graph, and when we report both stress and strain and the Young's modulus, even though this point and this point are both important, but when we report the maximum stress, not here, but we point out this point with the maximum value of the stress and the same strain. But when we report the Young's modulus, it is not this low. Considering this, we ignore this plastic region. We only consider this elastic region, which becomes the straightened line. So we just throw away this, and we draw the line, straight line. And the slope is the Young's modulus. Understood?
Therefore, to me it looks similar, both pictures. So what is the difference? No, pictorially.
This one.
Both
This one and this one.
So what is the difference?
When it's this one is the both character like plastic and elastic. That's why when stress is applied, then it's may with elastic behavior this material have, and some plastic deformation is occur. When stress is regained, when we withdraw, then it cannot come back. It's like this previous way. There is some kind of deformation is occur still.
So
Actually, our material is needed this kind of. Those have elastic and plastic both behavior.
So that is described as a color. The color is different.
Yeah,
Color is
this color and this color.
You
So
see that
what
this
is the difference between these two?
The color is different. That's why.
Only color?
These two. No.
So
Not
this one has a property of
property
this
of
one.
elastic and plastic. Both.
That one is
And this one has
Already
only
it
plastic
has some
behavior.
deformation.
Deformation. It cannot retain its previous form.
제가 궁금한 게 그 세 번째 게
영어로 얘기하는 거야.
Just demo this one. How it looks like inside the
last
material.
parameter is measuring value or calculating value.
Oh, this one?
네.
This one is
Measure.
we can theoretically calculate.
calculate.
Yeah.
How can we calculate?
We calculate?
So after measure, we can calculate. Calculate.
measure value.
Yeah, measure value. Sorry. Measure
아,
value.
얘가 어떻게 이렇게 나오냐고.
Not,
One
not
percent.
stop, not stop the motion, giving the force, just calculating the distance to the plastic.
I think he's asking this.
Oh, yeah. Because we cannot calculate this one theoretically. I will suppose it's theoretical. But when it's up to this value, when 0.2% is plastic deformation is occur. I mean, when it's the
No, that's not his asking. 이거는 그냥 이렇게 나온 그래프에서 지금 얘기하는 거 아니야? 이거 우리가 예측할 수는 없지.
그러니까 이게 0.2포인트 변화량 가진 지점에서 플라스틱에
Actually, it's a
플러프를
line.
써서
네,
대응을
알았어요.
하는 건지
어?
그러니까 0.2% 변화되는 지점에서
어.
엘라스틱 부분의 슬로프를
요렇게 때려왔네.
하는 건
어.
그렇게
모르겠네. 나도 그렇게 한 거 같은데.
20% strain. Yeah, theoretical. When
This is not, this line is not an experimental. This is
theoretical.
theoretical.
0.2% strain. We can
Oh, I
calculate.
see, I see.
0.2% from here we can how much deformation is occur. Which point is coming here. We can just parallel with
Draw the line just after that.
0.2% strain.
Okay.
Up to this point, 0.2% strain is occur.
I think we understand. I think we understand. Everybody understood, right? Maya understood?
This is yield value, right? We have to draw.
Yield point.
We have to draw 0.2% deformation, and we have to make parallel line.
Yeah, obviously parallel. If we don't do parallel like this one, then we can count here. Strain is called plastic strain to this yield strain. And the material properties, how it's the tensile professor already professor said that which value we use in the literature, this one up to this looks like one this is curve. The maximum stress is here, and we call this one the tensile stress. How much a material it shows its stress, how much they can take.
So we are not taking this value, we are taking this value.
Yeah, maximum stress is this value, and this one is the fracture point. But
That's where the material now is fracture breakdown.
fracture.
You understand, right? This is the maximum stress, right? Maximum stress, and this is for where the how's it counted?
This term also we can, in terms of strain, we can call it break of elongation.
break of elongation. 요 지점, 요게 우리가 보통 보고하는 그물질이 견딜 수 있는 가장 큰 힘이죠. 가장 큰 힘이고, 요 지점에 오면 이제 완전히 물질이 파괴가 돼서 이제 끊어지죠, 이렇게. 그러니까 더 이상 그래프가 안 나오는 지점이죠. 이거 elongation at break라고 그러죠. 여기 끊어진 지점이죠. 오케이.
Actually, it depends on the material. Sometimes its curve shows goes upward, sometimes goes below. It depends on material. Depending on the material, we can. The metal shows noticeable nagging, but in case of polymer, we don't see like this one, but it's narrowing like this one.
Are you gonna show the jig and the UTM?
Yes, how to use.
Are you gonna show?
Yes.
Okay.
And the polymer shows I will show how to polymer hands there. And in the tensile stress toughness, which property we have called toughness. Actually, it's a measure of how much amount of energy can hold before fracture, but within this elastic limit and after breakage or during this region, how much area it's covered, this called that material's toughness. And if we see here, the ceramics more tough and it can hold more stress. If we apply stress and after certain stress, it will break down suddenly. But if we apply stress on metal up to certain limit, it shows stress and strain, elastic like behavior, but after that it shows the plastic deformation. Permanent deformation is occur, and after certain point it's breakdown. And up to this area, if we found in graph, then we can find in this area we can measure this how much stuff is it, how much energy they can pressure they can hold. And in case of polymeric materials, we can find it shows very little elastic behavior, but most of the toughness is engaged from the plastic deformation. And actually, in our polymer, we need both elastic and plastic, both behavior. And the ductility also shows that how it's plastic and with elastic behavior. We can show the next slide. And if we see in different material, then we can find looks like in this one different curve like. If any curve shows very straight and after certain case it's break is occur, then we can told that that material is very brittle. They don't have ductility. They don't have malleability. We cannot shape it different way. And if they have a certain plastic behavior, permanent deformation, then we can say this one is moderate ductility, and some kind of material we can find it shows very long plastic behavior, and then we can call that material have very good ductile material and ductility. And this also can calculate like this way the area between this curve and this curve, and which material we can compare this one more ductile.
이 그래프를 보면 이 브리틀리스하고 덕탈리스를 이해할 수 있을 것 같은데, 브리틀 그러니까 두 개 다 지금 견디는 힘은 뭐 적지 않은데, 그 물질을 견딜 수 있는 힘은 적지 않은데, 브리틀하는 건 막이 어떤 물질 우리 고분자 막을 생각하면 그냥 아스러지는 거고요. 여기에서 아예 고분자 막자가 완전히 아스러지는 걸 얘기하는 거고, 덕타일하다는 것은 여전히 좋지 않은데, 이것도 좋지 않은데, 풍선이라고 그러나, 말을 한번 쭉 늘렸다가, 늘어나면서 이미 쭉 늘어난 거죠. 한번 쭉 늘어난 상태에서, 그렇다 끊어지는 것도 아니고, 그렇다 어스러지는 것도 아니고, 그렇다 복원이 되는 것도 아니고, 그냥 그 이상한 상태 좀 그렇게 있잖아요. 우리가 고무 같은 거 그렇게 쭉 늘어나면, 어느 정도까지는 그 원래 상태를 유지하다가, 더 땡기면 완전히 이상하게 되잖아요. 그거는 무슨 얘기인지 알 것 같은데, 헐렁헐렁하게 막 이렇게 돼 있는 상태를 그냥 쭉 가는 거죠. 그 상태에서 끊어지기 전까지. 이거 뭐 그래프 보면, I think you will understand the difference between the brittleness and ductileness. Both can absorb pretty high the stress, but the brittleness after a certain point the membrane got totally broken. Whereas the ductileness, although it loses its original point, similar pressure, but it's still not brittle. You know the like balloon, right?
High elongation, like high elongation and ductile materials.
High elongation, like a transparent film. Transparent film. If you apply some, it's not really brittle, right? So, but after certain pressure, it no longer has its original shape. It becomes very, you know what I mean? Huh? So useless, but still not brittle. Right? It has some plastic nature, but not its original that nice transparent film. And that goes very long, and that is the difference between brittleness and ductileness. Okay, go on.
And this actually for solid materials and for metal and other cases, the hardness, how it's resist. If we load upon here upon that material, or we force apply on material, then how it prevent this force. This called the hardness properties. If any metal ball we just fall down from certain height, then it may hit in the floor and there is some deepen or something. It's just get like this shape, and then the floor or the ball shows how much hard. If it's not that much tilt, then we can say that this material is harder. On how much its tilt is occurred, then we can calculate this one. Is it how hard or something? And regarding this value, we can divided the several materials. The most plastic material it shows hardness, less hardness, but with metal alloy is a little bit more, and the machine steel we can found its moderate hardness, and the 5 harder that we use for anything, for removing dust or the planing any surface, and cutting tool sometimes it's much more harder, and nitride steel that's much more harder, and finally if we, as we know, the diamond is much more harder, that's why we use for cutting glass. And I want to discuss in this slide how the polymer looks like, polymer inside, what kind of properties is changed and how it shows. Actually, we found when we take the UTM value for polymer, we get this kind of, already I discussed and also finally discuss this thing. This kind of curve shows the brittleness, but this kind of curve shows some elasticity up to this point, and there is some plastic behavior. Actually, we need this kind of behavior for our good polymer, and some polymer shows like this one, they don't have that much elasticity, but they have a lot of plastic behavior.
Like naphthalene.
Yes.
naphthalene membrane. 그러니까 팸에서 쓰는 나피온막이 이렇게 몇백 프로를 높여거든요. 몇백 프로. 이미 늘어난 쭈글쭈글한 상태인데 끊어지진 않아요. 또. 그래서 이런 상태로 몇백 프로. 우리는 다 요 영역인데 얘 혼자 이렇게.
And as we know, the polymer material is there is in terms of crystallinity effect, there is both polymer is semi-crystalline, and because inside of polymer there is some part of crystalline and some part is amorphous, and that's how polymer is crystalline. Inside of polymer there is some, as you know, polymer is a very big chain. They may fold it like this one and make like regular arrangement and make this area is crystalline, and it may, there is some physical bond, physical interaction, and it may tightly hold each other, and it shows much better mechanical properties. But in case of amorphous region, there is not that much regular arrangement. As we see here inside, there is some regular arrangement, and here is some irregular arrangement. This called is amorphous region, and this shows the plastic behavior when we apply force. As we saw here, the plastic diffusion takes place due to the bond elongation. When they just bond like this one, they just elongate this one, twisted this one, this bond elongation and the bond rotation. When their bond rotate, then there may be the maximum bond elongation is occurred that called elastic. And after when we just recover this stress, then it may again reform its previous state, and the angle strain is recovered, and then this way is called the elastic behavior. But when the intermolecular bonding in the crystal region or the amorphous region, when the polymer has another good behavior, we call it intertangle. When polymer chain is just
Intertangle.
and when we force the apply, then it just goes on over, and it's just long. Like if we see here, then you can found usually in the polymer there is some crystalline and some amorphous, and there is two adjacent chain is folded like this one. When we just apply force, stress, then the amorphous region first is just intercept and pass over one over and just go some elongation. But after certain case, when more stress is applied, then this segment, the crystalline segment, is separated like this one. And when we apply much more stress, then all the polymer chain shows like this one arrangement, and all the segment is arranged looks like linear and shows the maximum. And after that one, its structure is occur.
분자는 무기물질하고는 다르게 이제 결정성하고 어머포스 비결정성하고 섞여 있죠. 섞여 있는데 그 결정성이 크면 어떤 방향족 같은 것들이 많이 있는 고분자는 이제 당연히 이쪽으로 갈 거고요. 그다음에 알리퍼틱 같은 것들은 이제 탄성력을 나타낼 거고, 근데 우리 보통 이것도 너무 좋지 않고 이것도 너무 좋지 않고 장단점이 있기 때문에 그거를 그 화학적인 구조를 어떻게 튜닝하냐에 따라서 충분히 이걸 우리가 튜닝을 해야 되는 이건 그 고분자 기계적 성질이라는 것은 분자 간의 상호작용, 고분자 사슬과 고분자 사슬을 매크로 관점에서 나타나는 매크로 현상이기 때문에 우리가 고분자들의 구조와 그 모포로지라고 그러죠. 이게 뭐 필릭하고 울진들 이런 거죠. 하드한 데하고 소프트한 결정성과 비결정성들을 어떻게 잘 배열하느냐에 따라서 이 물질이 나타나는 똑같은 구조라도 배열하느냐 이런 정도에 따라서 굉장히 달라지게 됩니다. 그래서 우리가 그런 모포로지나 구조를 튜닝하는 게 굉장히 중요하죠. 예를 들어서 지금 인섭이가 하고 있는 고체 전해질에서 리튬의 가장 큰 문제가 리튬 덴드라이트가 양극 음극에서 리튬이 이제 추구하는 과정이 불안정하게 되면서 리튬 결정이 생기는데 그 결정이 쭉 자라게 되면 상대극 쪽으로 가면 두 정극이 닿게 되니까 그런 폭발하잖아요. 그렇죠? 그래서 이제 우리가 인섭이가 만들고 있는 고체 전해질인데 그 고체 전해질이 리튬이 자라는 결정을 막아줘야 되는 거죠. 그 역할로. 그걸 견딜 수 있는 힘이 얼마? 0.1메가파스칼 정도만 돼도 그 충분히 견뎌줄 수 있듯이 그 물질의 마다 그 용도에 따라서 그게 다 달라지고 또 그렇다고 해서 이건 너무 강하게 하면 당연히 너무 강한 쪽으로 가면 덴드라이트를 막아줄 수 있겠지만 상대적으로 물질이 덜 플렉서블해지니까 리튬 전도도를 잘 못해주니까 그런 밸런스를 잘 맞춰줘야 되는 뭐 그러한 것들이 있습니다. This mechanical property of the polymer is the macro, the properties of your polymer. So this is originated from the molecular interaction, like in a macro point of view. So in the polymer, as we know, there is always the crystal region and the non-crystal region, which we call as amorphous region. So there is always a mixture. So the way how the polymer, what kind of the polymer structure that we have, like aromatic, which is quite crystalline, versus the aliphatic, which is quite amorphous. So the structure is also important, not only structure, but the way how we orient these polymer structures, like we call as a morphology. So that gives a totally different behavior. Okay.
Actually, one term I forgot to discuss here, that one, in case of polymer, there is some certain intermolecular bonding. When this bonding is up to this stress, this bonding is remained. This stress is called elastic stress, and when this intermolecular bonding is breakdown, after that it was permanently deformation occur, and this due to this very weak bond, intermolecular bond, and the elastic behavior shows a very less amount. Less stress. When the bond is breakdown, then the plastic behavior is shown. And usually, if we fill in a graph how much strength of different materials, then we can find this. Our polymeric material shows this region, the red one, actually from very low stress to maximum we got 100 or this megapascals. But if we see all are different, but actually our target is we need to high strength as well as high break of elongation, much more ductile. We need both, elastic and plastic both behavior. And regarding getting these high properties first of all, I want to discuss how it's affect with this different temperature, and when measuring with red, how much force is applied, red is different than how it's curved nature. Actually, if we see the first graph, then we can find it described. If we change the temperature, measuring temperature, then the material behavior also changes, and from the curve we can find out if we see here, the temperature is near to zero, I mean 4 degrees Celsius, then it shows the material, polymeric material shows very stiff and it shows brittleness. And as we increase the temperature, it shows a little softer and it shows ductility. Then as we increase the temperature 30, 40, 60, 50, 60, then its ductility is increased and elongation and break is increased. And in case of same behavior also show when rate is increased. Then rate mean within 1 minute how much amount of elongation we wanna do this membrane of polymer. It depends on the rate. If we increase the rate, we'll elongate much more within short time. Then we can find its brittle behavior. But if we increase the time, the rate is slower, then we can find it's like the elongate behavior. And here is the.
So you're saying that as we increase the temperature, the PMMA becomes more
ductile, more elongate.
And that is due to? That is due to? Because?
Due to when we increase the temperature, maybe the polymer, the bond rotation and the molecular rotation is occurred. That's why it shows.
But then you have a more freedom. The polymer will have a more freedom to rotate at high temperature. Then it should go reverse, isn't it? Isn't it because what temperature we are talking about?
60 degrees Celsius.
And that is 180.
This one? This one 4 degrees Celsius.
4. Yeah.
Very low.
Where is it? Where this temperature 4 Celsius.
Yes.
And going
20.
20, 30, 40, 50, 60.
그러니까 그 온도로 가면 그 분자 자체가 훨씬 무브먼트 프리덤이 증가하니까 당연히 일라스틱으로 가야 되는 거 아니에요? 아까 잘못 얘기한 거 반대로 얘기한 거 같은데. Yeah, as we increase the temperature, the molecule polymer has more freedom to rotate, so it will become more flexible. So I think it's just a reverse. Okay,
No, sir, I told if we increase the temperature, it will more ductile and more
ductile. Okay. Can you talk about this one? This A?
Yeah, and if we see here the rate as I told, if we increase the rate, shows that as if the rate is slower, then it shows like this one. Rate is increased per second, the 10 millimeter, then it shows the brittleness and elongation is less.
How people measure high temperature and low temperature?
Different side of
Which
industrial.
they even did the SS measurement at different arrays.
Yes. How the arrays is affect in polymer as we take different and the judging
So this is from the recent paper. It's very interesting. You see that the same polymer, SCBS, with a very flexible polymer, styrene, ethylene butadiene styrene, so quite flexible. With at the end there is ammonium group. So as an NH exchange membrane, you see that they did the same polymer. They did RH measurement. You see that 0% RH, which means completely dry. Your membrane is completely dry, no water, zero water, very brittle. Same membrane. But as we increase the water, you see that it becomes very so much different, right? Because the water behaves as a plasticizer, soften your material. Everybody knows the plasticizer. Do you know what is it? Plasticizer, 가소제. Plasticizer is a small molecule within a big molecule, and that small molecule is soften your polymer, macro polymer. Suppose that you have a very big molecule, as if you add a small molecule like water in this case, that will break up your crystallinity and that will make your macromolecules softer. So it is like a softener. So that is called plasticizer. Okay. Plastic, we know the definition of plastic. So plasticizer, 가소제, 물질을 말랑말랑하게 해주는 그 거대 분자 사이에다가 조그만 분자를 넣어주면 결정선이 깨질 거 아니에요. 그러면서 이렇게 그게 물이 그 역할을 해주는 거예요. 어마어마하죠, 어마어마하죠. 근데 그래서 우리 막을 보고할 때, and this is why when we report the SS curve, always we should mention the Rx condition, whether it's dry, whether it's we usually measure 50%. That means we don't do anything. We just consider atmosphere as a 50% Rx. 따라서 저것처럼 우리가 막을 건조 상태에서 찍느냐 완전히 fully hydrated 상태에 따라서 완전히 바뀌기 때문에 우리가 물성 그 조건을 보여주지 않으면 정확한 정보가 안 되니까 항상 그 익스페리멘트를 보면 보고를 해주죠. 그래서 우리는 보통 50% RH에서 아무것도 안 해요. 그냥 상온에서 그냥 특별히 건조 안 하고 물을 빨짝 빼지도 않고 그냥 그 막의 특성 그대로 된다는 거죠. 오케이.
And here is some approach how we get better molecular mechanical properties for. We can take this kind of approach, then we can get good mechanical properties. Like longer chain, making long chain of polymer, then it shows good mechanical strength. Because of there is length, when a polymer length is increased, then it shows much more crystalline and it shows good mechanical strength. And as we see here, the tensile strength will increase. Even if we make the polymer is much higher molecular weight, then also it shows good mechanical properties. And if we see here, the tensile strength is increased with the molecular weight. As we know, the molecular weight is increased, then chain length also increased. That's why the chain are entangled or anchored better. If long chain is occurred, then it may hold more energy if we stress. And another thing is when it's much more molecular weight, then it may arrange very good and there show crystallinity. If we can make better crystalline, then it shows good mechanical property and stress in this one. The crystallinity also increase the tensile strength and another thing is annealing. Annealing means while we just making this polymer, then if we, in case of our case actually, when we prepare membrane, if we, it's slowly evaporate this solvent, it took a long time, then it can arrange, take more time to arrange itself, and it's called annealing mainly. And it may properly arrange and make good phase separated. It may show then good mechanical properties because annealing help to make very good crystalline part and it grows more crystal and it may increase this way to mechanical property. And already we know that in polymer.
It's mean how to reduce the temperature after making the polymer. If the cooling is very fast, then brittleness is there.
Yeah, then there is not orderly arranged inside of polymer. If we took more time, then it can arrange properly. And as already told, so the plasticizer, actually plasticizer is a very small kind of molecule that can trap inside of the polymeric chain and it may not give that polymer to arrange orderly. And that's why it shows the free volume inside of this polymer and it makes more flexible and shows much more elongation than and even if sometimes we get the polymer is more stiffer, then we can use the plasticizer for its softening. Reduce the brittleness, we can use plasticizer. And sometimes we found a few polymer is rubber-like, more plastic. Then we can add something additives to increase its stiffness or hardness. That things we call additives, but I didn't mention here. And by using cross-linking, if our polymer is not that much stiff, then we can use chemical cross-linking. It may create network and fix all the polymer chain to their position, and it may hold much more stress. And that's why in this approach we can also increase our polymer mechanical properties by using cross-linking. The reference, and this one how our instrument is used.
And this is the machine that we have upstairs. So it's called the UTM. That represent as a universal testing machine. What by the terms indicate, it can do. We do only SS curve measurement, but other than SS curve, we can do a lot of different studies, and that's why it's called universal testing. So it can do a lot of different testing as well. So 이 SS 커브를 우리가 메인으로 측정하지만 그 외에 뭐 찌그러뜨리는 시험도 할 수 있고 굉장히 다양한 걸 할 수 있어요. 그래서 그런 모든 걸 다 할 수 있다고 유니버설 테스팅 머신이라고 하고요. 사실은 우리가 안 해서 그렇지. 그거 can you explain?
Yes. Before measuring UTM, we need to cut off our membrane like this one. We have already cut it.
그게 어제 얘기한 거지.
네,
약간
네.
대책을 좀 강구하는 해야 될 것 같아. I think we just heard a lot of complaint downstairs, a lot of noise, and they cannot withstand anymore. So we have to find a solution. Everybody, from now on, everybody should go upstairs. Okay, when you cut the membrane.
Yes.
There's too much complaint from the line downstairs. Okay, no longer, understood. Okay.
And this membrane specimen length was 4 centimeter and its weight is 1 centimeter. But before placing here, we need to calculate this one using ruler. Just sign mark here from this side 1 centimeter and this side 1 centimeter, and we just need to measure thickness, how much it's thicker. And if we open this computer, then we can find in the screen this logo, and we can just click there and open this one. Like this diagram, we can find a dialog box, and then we need to create here for when we want to measure by mention or yourself name, then we create one method, and if we do like this, then we can find this. So here, then we can just by name we can set this one, and if you wanna do further how we control and measure this one, and then we can find here which unit we wanna use actually, Newton per meter square, or usually we use megapascal. That's why we use megapascal, and in case of strain, the percentage we are using, and the first, and then we can just click the next button, and you can get this dialog box. And here actually we look up here the sensor, how sensor is what, is it force or stress or how. Just we, instead of force, we can change here, click here stress, and the stroke then change to strain. And then we can go the next, and we can find here how much rate we wanna use. And sometimes we use 10 millimeter per minute. Usually people use 5 to 10 millimeter in this range. We just change here regarding your polymer. You can just change here, and you can go the next dialog. And here the specimen, how we define this one specimen is the name. You can give a specific name, and here the thickness, as I already measured the thickness, and weight already we have known 1 centimeter or 10 millimeter. And here we need to change unit. Usually we use millimeter. And here sometimes when we cut the membrane, it's not 4 centimeter, it's a little bit less or more. That's why we need to, using ruler, we can find out how much length inside of this to a terminal 1 centimeter. Sometimes it may happen 2 centimeter plus something. That's why we may use 21 millimeter or 20 millimeter, 20.5 millimeter like this one. And then we can go the next slide. and we can found this kind of how much they just predict what kind of properties of this graph. Nothing else here. We just show to next, and we can found here another dialog box, and here we need to change again this line of the x with x direction curve. What we wanna replace, actually in x direction we use the strain behavior. That's why we just x-axis the strain and the y-axis the stress. That's why we just change here force to stress and displacements to strain. And the below one, how much maximum stress is may happen in that polymer, we need to fix there. If we wanna do 100 megapascal or if much more deeper, then we need to may increase this maximum value, and minimum value is 0, no problem. But the strain we need to mention here how much we wanna use. As for my case, I use measure for ACBS. It shows very elongation behavior. That's why I use 400. And it depends on your polymer material how much it may maximum goes one. And we can just fix here how much strain is author, and then go to next. Then we can found this one. There is nothing. We just file is saved and certain name in the desktop, and then we can finish. And we go again to choose the select method. From there we can found here this way. But if you wanna use the several times and the specimen is different, then you can modify those terms here, and you can go like this one. And after that, when you set up this, there is two clamp. Between these two clamp, upper one terminal 1 centimeter is tightly hold, and the below one also we can fix here like a straight way, not tilt way. There is not cross way. And there is
perpendicular.
Yeah, perpendicular. There is two holder. We can hold inside of there is here is straight way, not like this. There is sometimes if we not concerned about this, may happen in the polymer. It looks like this way inside of these two pendant. That's
will break down easy.
Yeah, and it may not get uniform load inside of this polymer. And after the setup there, we need to focus here. We need to do the machine is 0. The force, the strain side 0 and strain as well 0. That's why first we need to push here to get here the 0 value, 0 megapascal. And after finally there is some beep is coming out from the machine. When it's become 0, then we can suddenly we need to push here to make it 0. It may 0 within very few minutes, but it takes little time to go 0. And after that, we can just start here manually in the machine, or in case of in the software, we can start button here. Then it runs and it gives us the final curve, and we can just after that getting curve, we just use to save like a save file in CVS file. I forgot to this next slide to CVS file, and we can take it out using UVS. That's
okay. Can you so 우리 스페시멘이 이렇게 생겼지? 이렇게 자르지?
위에 있는데
아, 이 가운데 이렇게 앉지?
예, 이렇게 되어 있는데
너무
이게
커서.
위에 부분에 손실 소모되는 양이 너무 많아서
아.
잘 못 써가지고
그래서
그래서 그 1cm, 2cm 짜리다.